Hello everyone. Welcome to part 6 of my line-following robot making series. In the previous episode, I demonstrated how to detect sharp turns, such as 90 and 60-degree angles, and how to execute and handle these types of turns effectively. So, in this video, I will show how to handle more common scenarios, such as cross lines, T-junctions, and stop points. If you're new here, make sure to subscribe to my channel and turn on the notification bell so you don't miss my upcoming videos. For this series, I'm using my custom-designed PCB carrier board made specifically for line-following robot. I have designed the board using 𝐀𝐬𝐸𝐴 software and printed it from JLCPCB. JLCPCB provides easy, affordable, and reliable PCB and PCBA solutions, empowering electronics engineers to develop projects efficiently. To place my order, I simply uploaded the Gerber file to their website, selected the quantity and color options, and finalized the order. You can get 5 high-quality PCBs for just $2. What's more impressive is that JLCPCB provides real-time tracking of the entire production process, so you know exactly what stage your order is in. After a few days, PCBs arrived at my doorstep. The quality of the PCB was top-notch. Then I assembled the board with the required component. Then I tested the PCB and everything worked perfectly. If you're looking for a smooth, affordable, and professional PCB manufacturing experience, JLCPCB is the way to go. You can order this board directly from us, and when you purchase it, you'll receive a fully functional operating system with an OLED display, which is completely free with the carrier board. To place an order, simply visit our Instagram, WhatsApp, or Facebook page. I recently designed and 3D printed a brand new chassis for this project. Now, I'm assembling all the components into this updated chassis. Once the assembly is complete, we'll move on to the coding part. To begin, I'm opening the code from the previous episode of this series, so I can continue right where I left off. Since I made some minor updates to the PCB design, including changes to a few pin numbers, I'll first adjust the pin definitions in the code to match the new black PCB design. In the last part, we discussed the section of the code responsible for turning execution. Specifically, we saw that when all sensors detect a white surface, the bit sensor value becomes 0. In this episode, I'll write new code to handle 3 important situations: stop points, T-intersections, and cross-intersections. In all of these cases, the sensors read a fully black surface, which means the bit sensor value is 255, as shown earlier. So first, I'll create a new condition that checks when the bit sensor value equals 255. When this condition is true, meaning all sensors are on the black line, the LED will turn on and the robot will come to a complete stop using the hard stop function. After that, I'll call the PID controller function inside the main loop, which activates when button 2 is pressed. Let's test the code. As you can see, when all sensors detect the black surface, the LED turns on, and the robot stops completely. Now, I need the robot to move a little forward from the stop point. To achieve this, I'll create a distance function to move the robot a specific number of centimeters. In the Turn tab, I'm creating a function named distance. To calculate distance accurately, I first need to determine how long the robot takes to move 1 centimeter. For that, I'll use a variable called time per centimeter, which is calculated by dividing the test time by the test distance. The total move time is then the distance multiplied by the time per centimeter, giving us the exact time the robot should move. Next, I'll define a variable called start time, which stores the current internal timer value of the Arduino using the millis function. Then, I'll create a while loop that remains active until the movement time is reached. During this time, the robot will move forward at the base speed to cover the desired distance. Then, I'm defining the test time and test distance at the beginning of the code. Next, I'll create another function called distance calibration to calibrate the movement timing. This function runs the motors for the specified test time and stops the robot afterward. I'll call this calibration function in the main loop when button 1 is pressed. Here I'm setting the test time to 500 milliseconds for a 30 centimeter test. Let's test this, using a 30 centimeter scale. When I start the calibration, the robot moves exactly 30 centimeters forward, confirming that 500 milliseconds is perfect for 30 centimeters. Now, testing the main distance function for 30, everything works perfectly. And then I conducted another test with a 10 centimeter distance, and everything works perfectly. Next, let's handle the stop point logic. When all sensors fall on a black surface, the LED turns on, and the robot moves forward by an additional 10 centimeters. After that, it reads the sensor values again to check the line condition. If all sensors are still on the black surface, it must be a stop point. So the robot should remain stop. To handle this, I'll use a while loop that stays active as long as all sensors detect black. The robot remains stationary and continuously checks the sensors. If any sensor detects a change, the loop breaks, and the robot resumes line following. I've also added detailed comments to the code to make each step clear. Let's test the stop point. Yeah, it works perfectly. Now let's move on to the T-junction. At a T-junction, after moving forward the set distance, the bit sensor value becomes 0. When this happens, I assign a direction value that determines which way the robot should turn, left or right. The turn execution code then uses this direction value to make the appropriate turn. Here, I've set the direction to left to turn the robot left when it comes to the T-junction. And the robot turns left at the T-junction perfectly. Then I'm changing the direction value to right. The robot now turns right. You can modify this as needed for your own setup. Finally, let's look at the cross intersection. In this case, after moving forward, the bit sensor value lies between 0 and 255. So, I'll write a condition for this range and set the direction value to straight, allowing the robot to move forward through the cross intersection. Let's test the cross intersection practically. As you can see that the robot successfully moves straight across the cross intersection. That's all for today's episode. In the next part, I'll cover automatic line calibration and the inverse line handling process. If you found this helpful, please like the video and subscribe to my channel. Thank you so much for watching the full video.